Section 1.3, mass, a measure of inertia. The inertia of an object is directly related to the mass of that object, how much stuff that object is made out of, the quantity of matter that is inside that object. If you have more mass, then you have more inertia, which means it'll be harder to change the object's motion or to get the object to start moving. Heavier objects are hard to move. Now, oftentimes, we relate the terms mass and weight in our brains. We consider them to be the same thing. But mass and weight are related, and that's why we often consider them to be the same thing. But they are not in any way, in a physical sense, the same thing. They are measuring two different things. Your mass measures what you are made of, how much stuff is there. Your weight is a measure of the force, the pull of gravity on your body as you stand on the earth. When you step on a scale, you have a little spring inside of the scale. You push down on the scale, and the scale measures your weight. It measures how much the earth is pulling down on you. In this context, your mass never changes. So not many people have been to the moon, but on the earth, you have some mass, and you experience some gravitational attraction, so you have some weight that you experience. When you go to the moon, if you could just teleport to the moon, you'd still be made out of the same amount of stuff, so long as the teleportation worked. You'd still be made out of the same amount of stuff, but you would weigh less. You would have the same mass, but because the moon is a much smaller object, you would experience a much lower pull from gravity. We'll discuss this further in a later chapter and explain why that's the case. But you can observe that it's the case if you go and watch old videos of the men on the moon from the Apollo missions. Wearing these giant jumpsuits, all this stuff on their back, and they're jumping way off the ground. And that's because they're used to Earth's gravity, where it requires some force to stand, and because their weight on the moon is about 1/6 of what it would be on the Earth. So, you only have to give 16% effort. Mass is what we refer to as a more fundamental measurement. Fundamental measurements in general are measurements of an object's fundamental qualities, the qualities that essentially define the object, its shape, what it's made out of, how dense that material is. Inherently, you recognize what inertia is. You've done this before when you shake Christmas presents to try to figure out what they are. You grab the present, you shake it. If it's heavy, it might be a book or something like that. If you shake it, it's light, Grandma got you clothes again. What you're doing is you're using that object's inertia to determine essentially its mass and its shape, to determine how it feels when it moves and how much it resists you trying to move it. If you close your eyes and someone hands you two objects that are the same shape and asks you to determine which one's gold and which one's aluminum, you get to keep the gold if you pick it. But if they're the same size and the same shape, they have different densities, which means they have different masses, different amounts of inertia. You need only just try to move them and know which one has the higher density. When we measure quantities in physics and in science in general, we use what are known as units. When you measure something, you have to be able to give it some amount, some quantitative value, but you also have to give it some value so that people know what you're talking about. If a friend asks you, how far is it from here to Florida? And you say 500, that's meaningless. In America, we would assume 500 miles. What if you're talking to somebody from a different country? So every time we make a measurement, we have to have some type of number and some type of unit that tells us what that measurement it is. Is it miles? Is it kilometers, meters, seconds? Some of the units that we use are referred to as fundamental units because they're measuring fundamental quantities. Some of the units that we use are referred to as standard units. They're standard units in particular measurement systems, and they measure fundamental quantities. The standard unit for mass is the kilogram. The standard unit for time is seconds. The standard unit for length is meters. The weight of an object is measured in the standard unit for force. Force is measured in newtons, which is written with a capital N. Newton is named after a person we'll discuss in the next chapter. Again, mass and weight are directly proportional to one another. If the mass goes up, the weight goes up, but they are not the same thing. We can treat them almost interchangeably on Earth because on Earth, the pull from gravity doesn't really change from place to place. Now, most of us use a scale to measure our weight. When we measure our weight in America, we measure ourselves in pounds. If you want to determine your mass in kilograms, start with your weight in pounds, and then multiply by 4.5. That will give you your weight in newtons. and then divide by the number 9.8. So a person who weighs about 190 pounds has a mass of around 87.2 kilograms. Sometimes we take fundamental quantities that we measure, things like mass and length and time, and we combine them to give us measurements of other quantities. We call these things derived quantities. So for example, another fundamental measurement of an object is its volume. Volume is how much space an object takes up. Box has a much different volume than a ball. We can then take the mass of the object, divide it by the volume of the object, and we can get a measurement of what's known as the density. The density is the mass per unit volume of the object. And so if you had 1 cubic centimeter of the object, you would know how much that object would weigh, and you would know the mass of that object.